The steelmaking process begins with our raw material, recycled scrap steel. The scrap is delivered in special trucks to one of our 2 melt shops at Harrison or Faircrest. For each heat of steel, we select the precise blend of scrap needed to achieve the desired final chemistry and properties. We use nearly 150 different classifications of scrap, each with specifications for chemistry and density. At the steel mill, scrap buckets are filled with a scrap blend. Lime is added to produce slag, and then the scrap is charged into one of our 3 electric arc furnaces. Electric arcs jumping across 3 carbon electrodes create controlled lightning in the steelmaking furnace, reaching temperatures of 9,000 degrees. In less than 2 hours, the highly efficient electric arc furnace has reduced the scrap to molten steel. While being melted, oxygen and other unwanted elements are absorbed and removed by the slag. Desirable elements, chromium, molybdenum, manganese, and others, are added to begin creating the proper chemistry to meet customer specifications. When the chemistry is right and the steel reaches 3,000 degrees, it's tapped into a transfer ladle. At the Harrison Steel Plant, we cast steel blooms in our strand caster, designed to produce extremely clean bar products. A ladle of steel is lifted 5 stories up. Protected from unwanted gases in the atmosphere by a shroud of argon gas, the steel is carefully metered out into a large tub called a tun dish. From there, it flows down into 4 rectangular water-cooled molds, electromagnetically stirred as the steel moves. As the steel begins to solidify, it is pulled down the molds and out to the runout table. The strands are straightened and cut into blooms of specialty carbon or alloy steel grades. We sequentially cast multiple heats of steel, making this a highly efficient, high-yield production process. The large bloom cross-section ensures a good reduction ratio with enhanced overall properties in the final steel products. At our Faircrest plant, steel is bottom poured into ingots. The ingot molds are arranged on an ingot car in a cluster around a central filling tube called the trumpet. A ladle is moved into position and the molten steel carefully flow controlled into the trumpet. The steel, protected from unwanted environmental gases by a shroud of argon gas, flows down the trumpet through runners at the bottom of the ingot cluster and fills the ingots from the bottom up. Bottom pouring creates steel with superior cleanness. This method eliminates steel splashing, which promotes excellent surface quality. Just poured ingots remain stationary as they begin to solidify, allowing any non-metallic inclusions to float to the top of the ingot, where they will later be cropped and removed. A heat of steel produces approximately 24 ingots, each weighing nearly 7 tons. The large 28-inch by 28-inch cross-section ingot provides a nearly 6-to-1 reduction ratio, down to 13-inch product, enhancing the steel's physical properties. At Faircrest, ingots are reheated to achieve uniform internal temperature, then transferred to the large reversing mill. The ingots pass between the grooved rolls and are reduced in size. This is called a reversing mill because after passing through the rolls in one direction, the ingot changes direction and passes through the mill again. With each pass, the size is reduced, moving the bloom closer to the final target dimensions. Besides just reducing the size of the billet, the rolling process also works the steel, reducing the cross-section, improving its crystalline structure, and strengthening the steel with each pass between the rolls. From these large mills, the bars will be further processed to meet customer specifications. At the Harrison Steel Plant, after the cast blooms have been reduced on one of the large mills, most of them are processed on our 10-stand inline horizontal vertical mill. The bars are rolled to the precise size, desired surface, and texture specifications. After rolling, the billets are cut to the desired length and transferred to the hotbed for controlled cooling. Round billets from one of our rolling mills are reheated in a rotary furnace. The billets travel once around the furnace and emerge at the appropriate temperature for piercing. The billets are transferred to the piercing mill, where they are drawn by 2 rotating drive rolls over a bullet-shaped piercing plug. This rotary forging process works the metal from the inside and the outside, creating more uniform grain structure. As the seamless tube is created, there is virtually no material lost. As the hole in the tube is created, the tube grows to approximately twice as long as when it entered as a billet. Tubes arrive at the elongator still red hot from the piercing mill. Each tube is worked between 3 rotating rolls. As the tube moves through the elongator, the tube OD is reduced to achieve the desired wall thickness. And as metal is displaced from the wall of the tube increases in length. Hot tubes are transferred to the reducing mill. Here, the tubes are drawn through sets of grooved rolls that are arranged at right angles to one another. The tube is uniformly squeezed, reducing the outside diameter closer to the desired final target size, while improving the roundness of the tube. Tubes can receive a number of finishing operations to change the steel's structure, grain size, tensile strength, and physical dimensions. Cold and hot working, turning, and thermal treatment processes are all available. Our 2-quench temper facilities provide significant capacity to heat treat steel bars and tubing to meet stringent customer requirements for strength, toughness, hardness, and uniformity. Process improvements in our induction thermal treatment facility reduce product distortion, resulting in maximum bar and tube straightness, and eliminate the need for additional cold straightening and stress relief. The continuous thermal treatment facility provides stress-free product through our hot straightening process, eliminating the need for additional stress relief operations. Our thermal treatment facilities and other steel finishing operations demonstrate how we use our steel knowledge to improve customer performance. As tubes travel through the ship preparation line, they are automatically gauged and measured. Cameras optically measure the OD size, while other techniques are used to ensure that the tube is the correct length as specified by the customer. The grade is verified with an inline spectrometer. Each tube is identified and marked with a unique customer order number that's stenciled on. These final checks prior to shipping provide a final verification that the customer is getting the correct products, the right steel with the right chemistry, and the right size, as ordered, with no mixes.